Alright, today we're talking just about two-dimensional objects. Two-dimensional.
I thought geometry was basically shapes, 3D
Well,
shapes.
Two-dimensional objects aren't shapes. They can still be shapes, right? Two-dimensional figures is what they call them. Alright, so basically just flat figures, okay? They have width and they have height, and that's about it. Alright, so that's all we're talking about. It's two-dimensional figures. So the first one we're going to talk about is, I'll tell you what, let's just draw one from scratch. Is that okay? I'm just draw one like this, like that, like that, like that. I'm not trying to draw it any, particular way. And like that. There we go. And let's group all that together. Alright. This thing right here is something we're going to be talking about quite a bit throughout throughout most of the book. Okay, this is the first time that you've heard this, but this thing right here is called a polygon. And basically every two-dimensional shape that we're going to be dealing with, well, I would say, I don't know if most, I'd say 95, 99% of the time, we're going to be dealing with things called polygons. Okay, and this is an example of a polygon. Now, they have a definition in the book. I'm not going to have you memorize the definition or anything, but a polygon is made up of, look at the sides of this thing. They all have to be what? They have to be straight lines, right? Or they're not just lines because they don't keep going forever. They do start and stop, so what would we call it? A line segment. Good. Okay, they all have line segments. Okay, and they all connect. Do you see it? Every one of these line segments connects to another one. They just don't connect anywhere. They connect at the endpoints. Good. All right. So each line segment is connected to another one at the endpoint. Do you see it? It's not like somewhere in the middle and you got a little bit of hangover. All right. There's nothing like that. So each one of these is connected at the endpoints. Each of those line segments. You follow me on that? Alright, so that's one thing that's true about it. They're also non-collinear. Do you remember that word? Non-collinear, what does that mean? Collinear means they all lie on the same line, so non-collinear means they don't lie on the same line, right? Okay, so look at this point here, A, B, and C. Now, if this was a straight line, that wouldn't really be the sides of our polygon, okay, because it would just be one side if I went from A to C and it was a nice straight line. Alright, so they're non-collinear points, okay, that's not that big of a deal. They intersect at the endpoints, that's a big deal, and each of those endpoints has a name, kind of like an angle, and it's not kind of like an angle, it is an angle, isn't it? Doesn't that form an angle right there? So what do we call that point where those two lines connect? We call the vertex, right? Okay, so we say this is the vertex of the polygon, just like we talked about earlier with an angle. But this time it's a polygon. And you're right, they do form angles though. Alright, that's an angle right there. Okay, and all these are angles. The whole thing is a polygon. Remember, it's all closed. There's no gaps. There's no open places. Because if there was an open place, then those line segments wouldn't connect at the endpoints, then would they? If there was a gap. Right? It's not like we have this hanging over. Watch. Let's see if I can match it up. It's pretty close. Not really. Scoops that up a little bit. Okay, what if we had something like that? Well, this endpoint is not being connected to another endpoint, is it? Right here of that little line segment. So that wouldn't be a polygon. But if we got rid of that, see all the endpoints connect to each other, that's a polygon. Everybody good? There's two types of polygons. This is not a huge deal, but they do mention it. There's a concave. Actually, I should have done this one first. And a convex. This one right here is a convex polygon. I'll show you why. I'm not going to use a straight line. We'll use a different color though. If I was going to take each of these sides and extend it out, watch. I'll show this as a dotted line. Alright, if I was going to take that side, extend it, this side, see what I'm doing? I'm just taking all those sides and extending them. Look where those extensions, those red dotted lines, intersect each other. They intersect each other where? Alright, it's going to take me all day. But you get the idea, don't you? I'm taking each one of those segments right there, each one of those sides of my polygon. I should have I should have written that down. That right there is a side of a polygon. Okay, each of those segments is called a side. But if I extended them all out, look, none of those dotted lines went inside the polygon, did it? Every one of them went outside the polygon. So if I was to extend all those sides, they're always going to intersect outside the polygon. That means that's a what? convex polygon. We call that a convex polygon. I would say for the most part, we're going to be talking about convex polygons. We'll hardly ever talk about concave polygons. But let me just show you a quick example, see if I can draw one, of a convex or a concave, I'm sorry, polygon. Let's just go different color. It'd be different. So let's see if I can draw one. So if we had this, we had this, this, this. There we go. That's still a polygon, isn't it? Because it's all connected, right? There's no gaps. All the endpoints are connected to another endpoint of another segment. They have sides. So yeah, we've got vertices, right? See the vertex? So yeah, it is a polygon, but look what happens. What if I was to extend the sides out? For instance, we're not going to do them all. What if I was going to take this side right here of that polygon and extend it? Look what happens. It goes through, doesn't it? And look at this side right here. That goes through also. So if it goes through the polygon, none of those went through. All those dotted line extensions, I took every side, didn't I? And extended it out. Let's see. Yeah, I took every one of those sides and extended it out. That one right there. And none of those dotted lines went inside. So that's convex. If it goes inside, it's what? Concave. You ever learn that in science about like not circles, but like lenses? Did you ever learn that in 9th grade science? No? A lot of you are still in 9th grade, aren't you? Okay, so you'll probably learn that in science class about concave and convex lenses. Yes? No? You don't ever remember hearing that? Anyway, well, I won't worry about that. But this one right here is concave, right? This is concave. We'll hardly ever deal with concave polygons. We'll mostly deal with convex polygons. But anyway, it's good to know the difference between the two. All right, here's another thing that we'll talk about. Let me pause this for a second and throw another picture up here. Okay, here's another polygon. All right, and how many sides does this have? 1, 2, 3, 4, 5, 6, 7, 8. So what's that look like then? 8 sides? Yeah, yeah, it's a stop sign. Exactly, right. Stop sign is what I was looking for. Right here, now, there's something that's different about this compared to what we've done earlier. I made sure, now I drew this previously, okay? I didn't do it right in front of you, but it was already done. But if I measured each one of those sides, what does it look like anyway to your eye about each of those sides?
One line equals friends. Yeah, they're all equal.
They're all equal to each other. So we put these little things. What do we call these little things? Do you remember? Little lines. Is that what we call them? We call them tick marks. Okay? Tick marks. All right? So we call them tick marks. So that means that all sides are equal to each other. Now, I also drew this. Now you just have to trust me on this, but you can kind of look at it, and it kind of looks like it. What do you think's true about all the angles here?
They're just equal.
They're all equal to each other. That's right. Now, look, just because all the sides are equal to each other doesn't necessarily mean all the angles are equal to each other. Did you hear what I said? Just because all the sides are equal does not necessarily mean all the angles are going to be equal to each other. I could have taken this. Well, I don't know if I could draw it or not, but trust me, you could probably draw this with all equal sides, and the angles aren't necessarily going to be equal to each other. All right? But I drew it so all the angles are equal to each other and all the sides are equal to each other. We call this, and we're going to be dealing with a lot of these kind of things, not just in this chapter, but at the very least, one other chapter that I can think of. We're going to be talking about this quite a bit, and this is called a regular polygon. Okay? Now, what does it mean to be regular? It means all the what? Sides are equal, or in geometry, a lot of times we say congruent, and all the what? Angles, right, are also congruent to each other. All right, so those two things have to be true to be a regular polygon. You with me?
What about interior points?
Interior points? What about them?
Well, it's like the angles that they can't have any interior point or
no, that's just talking about adjacent angles. We're just talking about whether these are the only two things that have to be true in order for this to be a regular polygon. First of all, it's got to be a polygon, okay? All the sides have to match up. They got to hit the endpoints of the other sides. But all the angles have to be equal and all the sides have to be equal. That's a regular polygon. Again, we're going to do a lot with that today, not necessarily. Demir, I'm up here. Thanks. All right, so right now, all we're doing is just learning what that thing is. Oh, let's name this thing. Watch. Each of these has a vertex, so each one is a point. So let's just name it A, B, C, D, E, F. I could have picked a smaller one, couldn't I? But that's okay. We picked 8 sides, that's alright. So A, B, C, D, E, F, G, H. I got them all. So if I was to name this thing, right, you know how we had a little symbol for angle, and we got a little symbol for line, and a symbol for all that other kind of stuff. We don't have a symbol for this. We just call it polygon, alright? Sorry to disappoint you. But we just use the word polygon. But how do you think we're going to name this? By all the points, okay? So if there's 8 angles and 8 vertices, right, or 8 sides, guess how many letters are going to name this thing, right? So let's name it A, what? B, C, D, E, F, G, H. Alright, that's a weird name for a polygon, but that's what it is. Alright, I could have called it Polygon Mr. Hammerhead, couldn't I? But it's probably about the same number of letters. Alright, so that's what we named that polygon. Now, of course, if it was a 3-sided polygon, or 4, or 5, or 6, you would just use that many points to name that particular polygon. Does that make sense? Alright, so that's polygon A, B, C, D, E, F, G, H. So there you go. Yep.
So even if there's a different amount of cells.
Yeah, if there was 5 sides, you would just use the 5 points that it's, you know, that make up that polygon. Yep. So that's an 8-sided figure, so it's going to have 8 letters associated with it. If it was 5 sides, it would have 5 letters associated with it. Make sense? All right. Let's see what else we got. Oh, let's talk about this. What if, now this is drawn so all the angles are equal, but what if just all the sides were equal and not the angles? What if all the sides were equal to each other or congruent to each other and not necessarily the angles? I don't have one of those drawn for you, but just use your imagination. What if all the sides were equal? Tell you what, I will draw one real quick.
It would be your regular polygon.
Let's do this, and I believe... Actually, I should have drawn this. Let's see if I can still do this. I don't know if I can or not. I'll just eyeball it. Okay, this might not necessarily be true, but watch. If this, this, and this were all equal to each other, are all these angles equal to each other? No, because look, what kind of angle is that? Obtuse. What kind of angle is that? Acute. So all the angles are not equal to each other, but guess what's true about all the sides? They are equal to each other. So if all the sides are equal, but not necessarily the angles, we call that equilateral. We're going to use that word a lot all throughout the year. Equilateral. Because lateral, we've talked about that word already this year. Lateral means sides. Equa, of course, you see the word equal in there, don't you? So equal number of sides. Or, yeah, not equal number of sides, but equal length of the sides. All the sides are equal in length. All right, so equilateral. What if you had a figure that was... all the angles were equal to each other, but the sides weren't necessarily equal to each other? And I don't know if I could even draw one of those. Yeah, it is possible. And I just can't think right now how to draw that thing, and I'm not going to try. But what if you had, I'll just write it down. What if all the angles... Yeah, that's true. A rectangle. Why didn't I think of that? Good call. That's an easy one. Watch. Watch this. What if I had this? Are you guys listening? Let's pay attention. Here's right here. And if I said that it's a rectangle, that means all the angles are right angles. But are the sides necessarily equal to each other on this? No, those would be equal, but these are definitely not equal to these right here, are they? So I've got equal angles, but I don't have equal sides. So if the angles are equal to each other, thank you. If I have the angles are equal to each other, I don't call this equilateral. What do you think I call it? Equiangular. Angular, okay? Equiangular. So let's write that down. Equiangular.
I kept seeing you right.
All right. So equilateral, all the sides, oops, that was supposed to be an underline, not a cross out, okay? Equilateral means all the sides are equal. Equiangular means all the angles are equal. If both are true, if both things are true, then it's a what?
Regular.
A regular polygon. All right, let's move on to something else.